So hello everyone, this is lecture 13 for the mathematical physics. In the last lecture we discussed about the existence and uniqueness of solution. Okay, and I already told you how we check if matrix has a unique solution. Okay, by writing the augmented matrix. And today we will see how we can check if matrix has no solution or infinitely many solutions by just seeing the augmented matrix. Okay, so I already did up to here. Now we'll start. Let's take an example. We have taken this example and then we write its augmented matrix. It's all coefficients here and the right hand side here. Okay, take the pivot element, make these elements 0, then take again this pivot element, make this element 0. Then after doing this we get this type of form, means we get 3 zeros here and 12 here. Okay, so when there was unique solution we were getting something element here and we write it like minus 50 x3 equal to this, then you can find the x3 value. Now here you can't write 0 x3 equal to 12 and that is not defined. Okay, so when you get this type of augmented matrix you will say that this system has no solution when there is zeros and there is some non-zero element. Okay, so here it was 0 0 0 and it is 12, so it has no solution. Okay, same we can take one more example for that. X is 0 4 3. Here we write this matrix. The augmented matrix will be look like this: 2 0 minus 1 2 3 2 0, and the right hand side 8 2 5. Then take the pivot element, that is not this, so we can just exchange the rows. I already told you why we do that. Okay, so take this down and take this up, so we just exchange rows. Now take this as pivot element and make this one 0. Okay, now take this one as pivot element, make this one 0. Then you will get this type of equation. You will get again 0 0 0 here and minus 4, so you can't write 0 x3 equal to minus 4, so that's why this type of augmented matrix has no solution. Okay, now let's take one more example. This is for the infinitely many solution. So let's see how can we say that a matrix or these equations have infinitely many solutions, just seeing the augmented matrix. So 3 2 2 minus 5 0.6 1.5 1.5 5.4 12 0.3 0.3 2.4 and the right hand side 8 2.7 2.1. Take the pivot element, make these terms 0. So how can you make? Just R2 will be R2 plus 0.2 R1 and R3 is R3 minus 0.4 R1. Okay, so you will get these elements 0. Then again you will take this as pivot element. Okay, then make this one 0. Then you will get after doing this you will get something like this, means now whole row is 0. Now there is no non-zero element, it's also a 0, so that's why this row has no meaning. And now you have only these two rows and you can see that variables are more than, means there are 4 variables and we have only 2 equations. So you can take any value, okay, for the x4 or x2, and that's how you can get any number of solutions. Means you have 2 only equations and you have 4 variables, so the other 2 variables can get any value, and that's how you can determine the other 2 variables. Means just assuming 2 values you can determine the remaining 2. Okay, so that's why, and that 2 can be anything, so that's why this type of equation has infinitely many solutions. Whenever you get something like this, whole row is 0 and number of variables are more than number of equations, then you will have infinitely many solutions. I hope you get the idea. Now let's take one more example. If it is given like for given set of equations x plus y1 y plus z1 x plus z1, then which statement is true? Equations are inconsistent, equations are consistent, and single non-trivial solution exists. Equations are consistent and many solutions exist. Equations are consistent. Okay, so first let me tell you what is consistent and inconsistent. I already told you, just let me repeat. When you have unique solution or infinitely many solutions, then you will call the system as consistent, and when you have no solution at all, then you will call the system as inconsistent. Okay, and when you have consistent, you have two choices, either unique solution or infinitely many solution. Okay, so when there is unique solution possible and which is non-trivial, then this option will be correct. Otherwise, if many solutions are exist, then this option will be correct, and if no solution exists, then this option will be correct. Let's check for them. 1 1 0 0 1 1, we just write the augmented matrix for these equations. That will be look like this. Then take the pivot element and make this one 0, you will get this. And take this one pivot element, make this one 0, and you will get the equation like this. So you can just see this augmented matrix and you can tell that it has unique solution. I already told you how. Okay, now this has unique solution, and unique solution, then it will be consistent, so this option will be correct. Equations are consistent and single non-trivial solution. Trivial solutions are those when you have all the values of variables are 0, x1 x2 x3 all will be 0, that will be trivial solution. So when they are non-zeros, then we will call it non-trivial solution. Now we end this here. Now we will start something new. That is linear independence of vectors. So if there are m vectors, then how can we say that these m vectors are linearly independent, and what is the meaning of independence? Okay, so let me tell you. So consider a set of m vectors. There are m vectors are available, a1 a2 and am. Each have same number of components, means each vector has same number of components, like a1 can have x plus y plus z, a2 will have 2x plus 2y plus 3z, means 2x I cap 2y j cap, means all have 3 components. It can be 4 also, it can be 5 also, but here we taken that all have same number of components. Okay, consider a set of m vectors each having same number of components, then its linear combination can be written as, we can write these m vectors with a combination like this: c1 any constant, c1 a1 plus c2 a2 plus c3 a3 cm am equal to 0. We can write the linear combination of these vectors like this. Okay, now how can we say that if these vectors are linearly dependent or independent? Okay, by just using this equation. If when we solve these variables and we find that all c1 c2 c3 all the constants came out to be 0, when this equal to 0, and that results only with when all ci's are 0, then we will call the system as linearly independent. If all ci's are 0 is the only solution of this equation, then these vectors are linearly independent, a1 a2 and am. Okay, but if they are not, means any one, at least any one came out to be non-zero, the c, then we call the system as linearly dependent. If at least one ci is non-zero, then this system are linearly dependent. So how can we say that? It's like if any one, means c1 is not 0, all others are 0, then we can write a1 as all came out to be right hand side minus, and c1 will be in the denominator, c2 upon c1 c3 upon c1, so we can write a1 as this. So now you can just observe and can say that this a1 is vector depending on these all vectors. Okay, that's how you can say that a1 is, means this system is linearly dependent. So all ci's should be 0 to say that all these vectors are linearly independent. Okay, I hope you get the idea how can we say that if some vectors are linearly independent or dependent. Now how can we say means how can we use matrix to tell a system or n vectors as they are independent or not? We will use a matrix. So for that let me first define you how can we check the rank of a matrix and what is the rank of a matrix. So the rank of a matrix A is the maximum number of linearly independent row vectors in a matrix. The maximum number of linearly independent vectors came out to be called the rank of the matrix. Means if there is matrix of 3 rows and there were 2 rows came out to be linearly independent, okay, then we'll call the rank of the matrix as 2, and this should be maximum, means the third one should can't be. So if all the 3's are independent, then we'll call the rank of the matrix as 3. Okay, so you will get the idea. We are going with this and we'll take some examples. So there is some theorems for the rank of matrix and independence of linearly. Okay, let's see the first equation. If there are p vectors are there and they all have n components each, and number of components are greater than equal to p, means they can be equal to number of vectors or can be greater than that. Okay, then they will be called linearly independent only if the matrix with these vectors as a row vector has rank p. Means there is this matrix and we have p vectors with n number of components. Okay, and rank of this matrix came out to be equal to p, means equal to number of vectors, number of p vectors. If rank came out to be p, then we call the system as linearly independent, and are linearly dependent if rank is less than p. If rank came out to be less than p, then we'll call it linearly dependent. So we'll see the example, just if you didn't get the idea. And there is theorem 2, p vectors with n components each, and if number of components are less than the number of vectors, then the system will always be linearly dependent. Okay, we'll see the examples and you will get the idea how we use these theorems. So let's say there are these three vectors a1, a2, a3. Then we can say that there are three vectors, then p will be 3, and each have three components, so n will be 3. Now write in the matrix, we'll get this type of matrix. Okay, now let's try to solve this. Means take this pivot element, make these 2 0, we'll get this type of form. Now take this pivot element, make this 0, we'll get this form. Now you can see that these all three are linearly independent vectors. Okay, linearly independent vectors. So what is the rank of this matrix is 3, because 3 linearly independent vectors we have. So rank of this matrix is 3, and how many vectors we have? P equal to 3. So rank of matrix is equal to p. So then we call the system as linearly independent according to theorem 1. According to theorem 1, the system will be linearly independent because rank was 3 and p equal to 3. Now let's take one more example. There are three vectors given a1, a2, a3. So p will be 3 and each have 3 components, so n will be 3. Now write it in this form. Take this as pivot element, make this 2 0. So these operations we applied and make these 2 zeros. Now take this as pivot element, make this one 0. So what we will get? We'll get something like this. Now what we are getting, that rank is not 3, means rank will definitely came out to be less than 3, because we have only 2 non-zero vectors here. So it can't be 3, it will always be less than 3. And what is the number of vectors? Is p. So according to the theorem 1, these vectors as a row vector has rank p and are linearly dependent if rank is less than p. So rank is less than p for this matrix, so that's why we call it linearly dependent. Rank will came out to be definitely 2 or 1 here, and we have p equal to 3, so rank is less than p, that's why we call it linearly dependent. Now take one more example, that is three vectors are given a1, a2, a3. So we have p equal to 3 and each have 2 components, so n equal to 2. So this second theorem, if p vectors with n components each and n is less than p, then they will always be linearly dependent. So we just can say that these are linearly dependent only by seeing these equations. Okay, now let's take one more example. This is a matrix. Take this pivot element, make this 0. Take this as pivot element, make this 0. Then we will get this type of form. And now you can see that we are getting 3. You can't make this 0. Try any operation, you can't make this 0. If you will make this 0, there will be non-zero somewhere here. So you have 3 linearly independent equations. Okay, so that's why the rank of this matrix will be 3. and how many vectors are we have? P equal to 3. So rank is equal to P. So we call the system as linearly independent. Now there is one more question. This type of question can be asked in the exam. 3 vectors are given. Okay, so this is alpha. So for what value of alpha these 3 vectors are linearly dependent? We need to find what value can be possible for alpha so that these system will be linearly dependent. So for we have 3 vectors, so P will be 3 and each have 3 components, so N will be 3. So matrix will be in this form. Now apply the operations. Make this take this pivot element, make these two 0, then take this as pivot element, make this 0, and we'll get this type of matrix. Now see, if this came out to be non-zero, then it has rank 3 and P is also 3, so we'll have the linearly independent. But the condition given in the question is that make this system as linearly dependent. So if we make this 0, then rank will be 2 and that will be less than P, and we'll call the system as linearly dependent. So if we make this 0, then situation will be verified, means according to the situation or the condition will be verified. So take this as 0 for alpha minus 31, then you will came out to be alpha equal to 31 upon 4. Okay, so if you take alpha equal to 31 upon 4 here, then it will turn out to be 0 and rank will be 2, which is less than P. So that will that's how we call the system as linearly dependent. So we find the value of alpha. So let's end here today's session. Okay, so just revisit and see the previous lectures if you are having any doubts. Okay, we will take these all topics individually and will understand them properly. So just be consistent. Thank you.